All right, can everyone hear me? Nice. All right. Hello, my name is Sean O'Connor, and I'll be giving the fuzzy type theory for opinion dynamics talk. First, though, yes, the Alt tab. Fantastic. First, though, I just wanted to give a brief moment to thank the rest of my members of my group who unfortunately couldn't be here today. I know how easy it is to see one person giving a talk and not really internalize all the other people that worked on it. So I just wanted to put some faces to the names and thank them. And unfortunately, Hans couldn't be here the previous week either. So I have his photo from his website. All right, so here's the idea. We want to model opinions in a way that sort of keeps track of how those opinions were formed. So the idea Paige had was to kind of almost do like a proof relevant opinion modeling, where we can represent opinions as terms of some type. And so we can evaluate how a specific term was constructed, perhaps looking at specific constructors, and hopefully get a way to infer how exactly someone came to have an opinion just from the opinion they currently have. And to do this, we're going to model types as opinions, and then terms as proofs of or reasons for opinions. And so the reason we're using terms here is because you could have someone have one opinion and have another person have the same opinion, but they could have arrived to that opinion in two completely different ways. And so we want to be able to distinguish between those cases. And then finally, we want fuzzy logic as a way of sort of talking about the degree that someone holds an opinion. Because you could have someone hold the same opinion, but like to different degrees, depending on the amount of evidence they have, or maybe the situation they attain that opinion. And so we have this nice diagram here, sort of talking about the differences between binary and fuzzy logic, and then propositional and type theoretic systems. So we can think of this as, so type theories have categorical semantics, which is sort of this category that can be used to reason about the semantics of the type theory. In the case when the category is enriched over the Booleans, or in the case of posets, we actually get that this corresponds to natural deduction. So natural deduction is almost like type theory, except we don't actually worry about the terms of an individual type. In the case when it's enriched over set, we get that this is just simply type lambda calculus. And that's a pretty standard construction, if quite involved. We haven't fully worked this out, but we think that in the case when we enrich the category over the interval, so from 0 to 1, this corresponds to fuzzy logic, except it would be like a natural deduction form of fuzzy logic. We actually chose not to go into that too much because we wanted to focus on the next one, which is when we enrich the category over fuzzy sets. So in this case, each Hom set will be a set paired with an assignment of fuzzy values to each element in the set. So this right here is what we're focusing on. So to sort of get to sort of figure out what a fuzzy type theory is, we're going to use this back and forth between type theories and categories. Because we can take the syntax of a type theory with all its structural rules, and we can look at the categorical semantics of it, but we can also do the reverse. If we have a category that sort of satisfies the semantical properties that we want, we can try to derive what the structural rules should be. So in some sense, what we're doing is we're going to take the standard category of semantics for a simply type lambda calculus, or hopefully later on dependent type theory, and then we're going to enrich that category over fuzzy sets, and then try to work backwards to get a fuzzy type theory from there. And the whole reason of doing this is to try to make as few choices as possible in some sense, so that we have less of an issue of making a bad choice and then having consequences down the line. So we can obtain a category from a type theory where the objects are context, and then the context morphisms are a list of terms. So specifically, if you have some context gamma and a morphism into a context delta, what that means is for each term in the context delta, we could derive that from the context gamma. This is important mainly for, this is how we do substitution rules in the category of semantics. To give a bit more background on this, in case you're unfamiliar with it, a type in some context is a specific class of maps called projections from this term right here, gamma.a into gamma. So this says that A is a type in the context gamma. If you're wondering about what we mean by projections here, this is formalized specifically in C systems, which sort of clarifies how we can actually talk about gamma.a, because that is purely syntax. That does not actually correspond to some sort of product or concatenation operation in the category. We have terms. So a term of a type A in a context of gamma is a section of a projection. And the reason for this is we want, in our type theory at least, terms to only have one single type. And this works because sections are only sections of a single projection, which is nice. And then to do substitution, we're also going to do pullback along projections. We'll see an example of this later, but we can do similar things for all the different structural rules in type theory. All right, so our strategy is enrich the categories and then read the type theory from there in the same way that we would read the type theory from the standard category. So we're going to let V equal the category of fuzzy sets, and this will be a monoid because it's sort of just taking sets and then applying the interval category, which is a monoid in itself. We're using the less than or equal to relation because we want this to be ordered. So objects are going to be pairs. So objects in V are going to be pairs of a set and then an evaluation of each element in that set to some fuzziness value. And then morphisms are going to be order preserving set functions. And the hope here is that we can work between fuzzy type theories and V categories. And we're going to understand this by looking at the standard way categorical semantics are used, and then trying to get fuzzy type theory from there. Okay, so some reasons to do this is we're trying to model opinion dynamics using this. And the way we're going to do this is have each agent in the system have their own V category, so their own category enriched over fuzzy sets. And the hope then is that context would be a set of beliefs that this agent has, and then a type in context would be a set of beliefs and it's like premises that an agent would have. And then a term of a type A would be a proof of the belief corresponding to A. And because we want definite beliefs, we're going to actually have non-fuzzy types. This was a bit of contention at the beginning. I was in favor of fuzzy types, and that turned out to be wrong. So glad we didn't do that. But now we do want fuzzy terms because we want people to be able to have different strengths of an opinion. And so we're going to try to find a way to have non-fuzzy types, but fuzzy terms. And so the way we do this, once we get to the math, is having an axiom that types are not fuzzy, which corresponds to the evaluation of every projection map to be 1. However, we quickly run into an issue. The way sections are normally defined in non-enriched settings is such that the composition with the projection is the identity. The issue here is that if we want this to hold true in our enriched case, we get that the morphism from gamma into gamma.a, which corresponds to the section, would have a fuzziness of 1, which means we don't get fuzzy terms. And that is not desirable. We do want fuzzy terms, and so this kind of section is too restrictive. So what we do is we introduce alpha sections. Alpha sections are just sections, except that we relax the requirement that the product of the evaluations is equal to 1, and instead it's just greater than or equal to alpha. One nice thing about this is this actually gives us a nice little rule where given a term of type A with fuzziness alpha, if beta is less than or equal to alpha, we can actually derive that the term also has a fuzziness beta. And one way to think about this is if you're confident in 80% something, you're at least confident in 50% of it. So this is a nice little rule that we do use time to time because it sort of aligns with composition, because composition here isn't exactly strict. When we compose two morphisms, it doesn't actually need to be exactly the fuzziness of the resulting morphism. It just has to satisfy a less than or equal to relation. All right, so classically, the way we do substitution is using pullbacks. This does not work because in the rich case, you need to use something more complicated called weighted pullbacks. And this is a special case of weighted limits, which is how we actually calculate the weighted pullback and what the universal property is. So as an example of what a weighted pullback is, we can actually just look at standard categories where we view them as set enriched categories. So normally with a pullback, we get this bijection right here, where we can actually view this, where we sort of view each of these objects as being mapped to by the terminal object. So it picks out a single morphism in there. And so from the perspective of weighted pullbacks, we say this is a 1-1-1 weighted pullback, where 1 is just the terminal object or the singleton set. So to try to work with fuzzy substitution, we need to find the reasonable weights for the substitution structural rule. So specifically, this will be a requirement we impose on the category. We say for this category to work, we need to have these specific pullbacks or these specific weighted pullbacks. We can't work with the terminal object. That's a bit too restrictive. But what we can do is we can work with the singleton set and then a constant evaluation map for some x in the interval. And so this actually works kind of nicely because given a morphism fuzziness alpha and a morphism with fuzziness beta, we can require the weighted pullback where the first weight is has fuzziness alpha, second weight is fuzziness 1 because that's this diagonal map. We don't particularly care about that. And then the third one is fuzziness beta. And using the whole weighted limit definition and everything, we actually get that the universal property is such that this morphism right here has this complicated weight. The important thing to realize is just that the top map delta, the fuzziness of the top map delta is divided by alpha here. And so division here is if alpha is 0, we can just ignore it. And if it's less than delta, then because of the minimization, we just get 1. So this all works out. It's all still within still within the interval. So quickly, we realize something weird happens with this. We can first take a look at this pullback. This is not anything unique. This is just kind of a double projection. And because projections are preserved by pullbacks, this is still a projection. But we do get this map with fuzziness 1. And this sort of corresponds to variable repetition. So given a term of type A, we can produce a term of type A with fuzziness 1. Essentially, we don't lose any information if we already have a term of that type, which is all standard. Like this is what we expected. However, if we then can produce a term of type A with fuzziness alpha, we can look at this specific pullback diagram and get that this morphism right here, the top diagonal one, has a fuzziness of 1, actually, because we divide alpha up here by alpha down here. And so we get this rule over here, which looks really bad. It kind of looks like fuzziness collapses. That given any term of some fuzziness, we then get a term of fuzziness 1 in that same type. This is really not good. However, Paige actually noticed that a trick here is that this is not the same object as this. It is the same object when you work with projections. So in the case of the non-fuzzy categories, this is a projection. This is the same object. You can prove an isomorphism, but we can't actually do that here. And so what we can do is we can denote this object as 1 dot A alpha. And so this actually sort of resolves the crisis. I should have fixed that. Sorry about that. This actually resolves the crisis here because we can read this rule down here, which says given a term in type A with fuzziness alpha, we can derive a term of type A sub alpha of fuzziness 1. We can read this as given a proof of A with confidence alpha, we can prove with confidence 1 that we can prove A with confidence alpha. It's kind of complicated, but it doesn't break everything. So I much prefer that. So this is actually the full rule of fuzzy substitution. Do not read it all, please. This took us an entire afternoon to work out. It was not fun. And we had to do it twice after we found the mistake earlier before we found the resolution. So this is just everything. What we can basically say is that we can do a substitution here and we sort of carry around this alpha because given this context gamma, we have to first create a term A with fuzziness alpha, and then we can create the term in B. So this is a bit complicated here, but it does work with everything else that we need. Before, we also thought there was going to be an issue with composition, because if we derive composition from just the concatenation of from just the composition of morphisms, we'd get a different result than if we did it from the pullbacks. But actually now, because the pullback doesn't actually preserve the object, we don't have this issue. So this all works, and we're all very happy for it. So we can prove now that such a V category satisfies all the structural rules of type theory. We haven't yet done the dependent case. That is a bit more complicated because you can't just look at sections. You have to look at vice categories. But we can have categories to encode the logical system of the agents in our system, which is great. And so the dynamic that we now want to model, so we have Jacob Hansen and Robert Gerst uses a cellular sheaf over vector spaces to study opinion dynamics. And then Hans Ries, which is our TA, and Robert Gerst study cellular sheaves into lattices. And so now we want to explore cellular sheaves into these sort of VCATs, where we can sort of view each agent as having their own type system, and then the region they discourse is their own type system. So this is all our future work. We'd like to work on that. Unfortunately, we only just figured out the resolution to our issue at the end of the week, so we didn't have much time to do any of the dynamic work. but we're going to try to do that in the future. And so next, we're going to try to do enriched categorical interpretations of dependent fuzzy types, and also address definitional equality. We haven't really talked about that, but we could see, if there's any fun things we can do there. We can also replace 0 to 1 by any ordered monoid M, which is nice. I was talking to a colleague about how we could replace it with 0 to infinity with addition and greater than or equal to as the relation. You can maybe model distance or something like that, which would be interesting. And then we're going to also explore the dynamic side more, hopefully once we get a better understanding of the dependent fuzzy types. All right, here are our references, and thank you.
Hello? Can I ask if you have thought about what you might need to add, or whether this is compatible with a probabilistic logic where you maybe talk about coproducts as disjunctions or something like that?
Yeah, so the initial idea, well, my initial understanding of the fuzzy logic was that it was just a way to do propositional logic. But you run into an issue in that probability isn't categorical, at least not like the naive way you'd think about it. Like, for example, if you know that the probability of B given A, and you know the probability of C given B, you do not know the probability of C given A. And so you need to be a bit more careful. We have been thinking about potentially modeling probability as morphisms from A to A intersection B. So in that case, you sort of maintain the context. You never run into issues where you sort of weaken, because you can't weaken in the probabilistic setting. So we've been sort of thinking about how we could add notions of probability, or maybe choose our category to begin with so that it corresponds to probability. But we don't have anything solid there yet.
Okay, thank you. That seems like a very interesting line of work. Do you have any idea how this relates to, traditionally people study this logic for belief in modal logic? There's quite a long tradition in that. Any idea at all how this is related?
Unfortunately, no. I have not much experience with modal logic besides knowing that it exists, and it's very impressive. Yes. So I don't know exactly how this would relate to it. I think the idea with trying to do fuzzy type theory was building off of fuzzy logic, which is something that exists. But we kind of tried to go at this from starting with like a specific thing and then seeing what we can get from there with like I mentioned before, making as few choices as possible. So I don't know how we would sort of, I guess, compare this to a modal logic case. It'd be very interesting to see if there's like a really nice correspondence in that. That'd be very cool.
Yeah, okay, thanks.